Okay, so this week, well, it's day one of week 2, so I figured this would be a good time to start with 7.1, which is the first out of the 3 sections you would need to read this week. And 7.1 is linear and nonlinear systems of equations. If you've taken college algebra here at Grantham, which David, I know you have, then this is all going to be review. But I know we have some students that this is their first class with Grantham, so they may or may not have seen this before. So we're gonna we'll go through it. So 7.1 covers using the method of substitution to solve systems of linear equations in 2 variables. Using the method of substitution to solve systems of non-linear equations in 2 variables. I'm going to just highlight the 2 differences of those. So these are both using substitution, but one of them is linear, the other one is non-linear. Using a graphical method to solve systems of equations in 2 variables, and then use systems of equations to model and solve real-life problems. Now, if you've solved systems of equations before, then you may be wondering, well, what about elimination? So elimination is covered in section 7.2. So we're only going to use substitution in this particular section. And then when you get to 7.3, that's where you're going to get into 3 equation systems, and there most of the time we use a combination of both elimination and substitution. So I'm going to just start with the basics, just to introduce what a system is. And just as a side note, a system of equations is also called a simultaneous system, or simultaneous system, or simultaneous equations. So simultaneous just means that you're looking at all the equations at the same time. In mathematics, we generally don't use the term simultaneous equation or simultaneous system, but that is something you'll see in engineering. They use that phrase. So I just wanted to point that out. So a system is a set of 2 or more equations. And so the bare minimum to have a system is 2 equations. And you basically want to have the same number of equations as you have, or the same number of variables as you have equations. So 2 variables means you need to have 2 equations to solve. If you don't, you can't solve it. And if you have 3 variables, then you need to have 3 equations in order to solve it. It's okay to have more equations, you just can't have less. So if you have 2 variables in 1 equation, you don't have enough information. But if you have 2 variables in 3 equations, you have enough information to solve it and extra information that you don't need. So when we write a system, we have a curly brace, and then we put the equations on top of each other. This curly brace is required. If you don't write that, then you don't have a system. That is required for system notation. And when you are doing the homework assignment this week, you have to write down the system because you are not given the equations. And so the first step would be to determine what the system is. That means determining the equations. And you need to put them in this form. So if I don't see the little curly brace or it's not written in the correct form, you're going to lose points because you need to be able to communicate the mathematics correctly. And so that's part of knowing the symbolism and how things are written. So we always write a system by putting curly braces around all of the equations that we have, and then the equations are basically stacked on top of each other. And the solution to a system is an ordered pair. So if you have 2 variables, you have an x and a y value. Now I'm going to briefly bring up Microsoft Word because I just want to demonstrate how you can type a system into Word. You're not required to use Microsoft Word at all. You can write it, you can do it on paper and then scan it. But for some people like to use Word, and so I just want to demonstrate how you can do that. So if you have a downloaded version of Word, it comes with the equation editor. If you're using Office 365 online, it doesn't. You have to insert, you have to add a plugin. But if you're, as long as you have the downloaded version, and mine, I think it might look a little different than some versions. When you go to insert and you insert an equation, and then you get this equation box, in order to do a system, you go to where it says brackets, and then it always takes a little bit to load when I'm sharing my screen. And so we want to scroll down because we just have a single bracket. And actually, we want to scroll down to where it says cases and stacks. So the first one here, that would be a system with 2 equations. The second one would be a system with 3 equations. And so you would click here, and then you can just click inside the box to type your equation. And then you just click inside the second box to type your other equation. And then that's how you write a system in Microsoft Word if you choose to type up your work that way. But that is not required. I just wanted to demonstrate that for those who may decide to do that. So that's part of the requirement. You have to have that curly brace. That's very important when you are indicating whether you have a system. So the method that 7.1 covers is the method of substitution. So the method of substitution, this is a 5-step process. So the first step is to solve one of the equations for one variable in terms of the other. So you take one of the equations are given, you either solve for x or solve for y. And it doesn't matter which one you solve for, you want to just pick the one that looks easiest. And if it's already solved for either x or y, then great, you don't have to use that step. Step 2 is to substitute the expression found in step 1 into the other equation. And then when you do that, you now have an equation with only one variable. So now that you're in one variable, now you can solve that equation. So that's step 3. Step 4, we back substitute the value obtained in 3 into the expression in step 1. So what that means is basically you take your answer from solving and you plug it into the first equation, the one that you solved for, because that will be an easy one to plug it back into. And that will allow you to find the second solution, because systems of equations need to have as many values as a solution as equations, 1x, 1y if it's 2 equations. If we have 3 equations, it's usually x, y, and z. We go in alphabetical order, starting with x. And you can always check your work, and you can check your work by either plugging your values into both equations. So you'd plug your x and y numbers into both equations. Or another way is to do it by graphing. Graphing is a great way to check your solution, but it doesn't work well if your solution is not whole numbers. Graphing is great if you have whole number answers, but anything with decimals doesn't work so great. So I have an example here, and we're going to solve this using substitution. So I have a system, 2 equations, 2 variables, x and y. We have x minus 4y equals negative 11, and x plus 3y equals 3. So we want to solve one of the equations for x or for y. It doesn't matter which equation, and it doesn't matter which variable we solve for. So you can choose anything you want, either method. When I look at this, and I'm going to try to explain to you, like you want to try to make your work as easy as possible and as efficient as possible. So both of them don't have a coefficient in front of x. So solving for x would be the easiest because I don't have to divide by anything. Whether I use the first equation or the second equation, it really does not matter. So if it doesn't matter whether I use the first or the second, then I usually just use the first equation because that's just the first one in the list. So our first equation, we have x minus 4y equals negative 11. And so I want to solve this for x so that I have an equation in terms of x that I can plug into the other equation. So that means I need to add 4y to both sides. So this gives me x equals negative 11 plus 4y. And I could write the y first. I could do 4y minus 11. It really doesn't matter. So that's the first equation. The second equation we have is x plus 3y equals 3. So I'm going to be taking what I have solved here for x, the negative 11 plus 4y, and I'm going to plug it in for x in the second equation. So instead of x, I now have negative 11 plus 4y plus 3y equals 3. So step 3 is to solve that equation. So to solve this, I'm going to add my like terms, my 4y plus 3y. So I have negative 11 plus 7y equals 3. And now I'm going to continue solving for y, so I'm going to add 11 to both sides. So that gives me 7y equals 14. And then I divide both sides by 7. I get y equals 2. So once you get that, you are not done because we need to find both values. You have a y and an x. So now that I have y equals 2, I need to go back to my first equation and I'm going to plug it in for y so that I can figure out what x is. Or I can also plug it into my solved equation, which is actually the easiest one to do. So basically you're taking your answer and now you're replacing y so that you can find what x is. So x is equal to negative 11 plus 4 times 2, since y is 2. So we get x equals negative 11 plus 8, which gives us negative 3. And so then your solution is always an ordered pair, negative 3, comma 2. Now because we got whole numbers here, we got integers, we didn't get any fractions, this is a great system to solve by graphing and to verify by graphing. So I'm going to bring up Desmos. I don't want to cover up the actual problem. There we go. And so in order to graph the system in Desmos, you're going to graph each equation separately. So I have x minus 4y equals negative 11, and then x plus 3y equals 3. And you can see on here where they intersect. So you can see the intersection points. And I highlight that because it finds it already, and it says it's negative 3, comma 2, which is the answer we got. We got negative 3, comma 2 there for our ordered pair. So that's a way to verify that you did your math correctly. If it matches on the graph, then that is the solution. So the solution is basically saying we have these equations and we're looking for where they are both true. So we're looking for a point that works in both equations. An example of this in the real world would be a break-even point. So maybe, let's say, now this doesn't make sense because it's in the negatives, but maybe the blue line, if you're in the business world, that could be, I don't know, well, that may not even be going down, but like, well, you could have one line being profit, one line being the cost, and so then you're trying to find where your cost is equal to the profit, so you break even, and then, you know, if anything beyond that point, then you start making money and having some revenue. So, or is it, no, it's the other way around, revenue and cost, and then that would be profit after that. But that would be like the break-even point, basically. Where are they equal? And then that helps you figure out where one is better than the other. Are there any questions? Okay. So the next part is nonlinear systems. So nonlinear systems are when at least one of the equations is not a line. So what we just solved was a linear system. They were both equations for lines, but you could be solving systems with things that are parabolas. You could have circles. You could have things with e or natural log or absolute value. You can get pretty complicated. And so those are all called nonlinear. And most of the time, nonlinear systems have more than one solution. So instead of having one ordered pair, there will also actually be like two or more ordered pairs as a solution to a system. Though it is possible to get one solution to a nonlinear system. You have to get it right in the perfect spot in order to get that, but it is possible. So the best way to solve a nonlinear system is through substitution or graphing. You could do elimination, but it's usually a lot harder to do. So substitution is the best method. So here is my example of a nonlinear system. So we have 3x plus y equals 2. That one's linear, but the second equation is cubic. It has x cubed minus 2 plus y equals 0. So as soon as you have something that has an exponent on it, it's no longer linear. So now this is a nonlinear system. So when you're doing substitution, you generally don't want to plug in to the variable that has the exponent, because if you're plugging into something squared, that means you're going to have to square whatever your expression is. If I plugged in an expression for this x cubed, that means I would have to cube something, and that's a lot of work. So I don't want to plug in for x. I want to plug in for y. So that means I want to solve the first equation for y. I'm going to keep it in terms of x because that's what has the exponent. And really for us, the first equation is actually quite easy to solve for y. So all I have to do is subtract 3x from both sides. So I get y equals 2 minus 3x. So I'm going to replace y in my second equation with 2 minus 3x. So we have x cubed minus 2 plus y, which is 2 minus 3x, equals 0. So now we want to combine like terms. The minus 2 plus 2, that actually cancels out. So this is going to work out very nicely for us. We have x cubed minus 3x equals 0. Now we need to solve a polynomial. So when you're solving a polynomial that's equal to 0, you want to factor. So here I can factor out an x, that is my greatest common factor, which leaves me x squared minus 3. So I have x times x squared minus 3. Now x squared minus 3 can't be factored. So now this is where I'm going to use the zero factor property by setting each factor equal to 0. So I have x equals 0. And then I get x squared minus 3 equal to 0. And now I want to solve each of these for x. So I already have one solved for x. I have x equals 0. But now I need to solve my quadratic here. So if I add 3 to both sides, I get x squared equals 3. And then to solve this, I need to take the square root of both sides. And when we take the square root, we get a plus and a minus. So I get x equals plus or minus the square root of 3. So the key here, the important thing to notice is that the x cubed, so an exponent is 3. And this tells us we're going to have 3 solutions. Sometimes you may have less than that, but generally the exponent that you have in your system indicates how many solutions you have, or at least that's the maximum number of solutions, because it is possible to have less than that, but most of the time it's going to be equal to the same. So since we have a cubic, that's 3 solutions. So we have 3 x values. We have 0, we have negative square root of 3, and we have positive square root of 3. So we need to find the ordered pair for each of these three sets of values. And for that, we're going to plug it into this y equals 2 minus 3x so that we can find the y value now that we have the x value. So I'm going to do this on the next slide. So we have x values of 0, we have negative square root of 3, and we have positive square root of 3. And we are plugging this into y equals 2 minus 3x. So y equals 2 minus 3x. So it's going to be 2 minus 3 times 0, which is just 2. So we have one solution, which is 0, 2. Second solution here, we're plugging in negative square root of 3. So I have 2 minus 3 times the negative square root of 3. So a negative times a negative is positive. This is going to be 2 plus 3 square root of 3. Now, we don't want to approximate this, so we are actually going to write our answer with these nasty radicals. So our x is negative square root of 3, and then the y is 2 plus 3 times the square root of 3. And then the third solution is we have a positive square root of 3, so it's 2 minus 3 times the square root of 3, which gives us 2 minus 3 square root of 3. So our ordered pair is the square root of 3 and 2 minus 3 times the square root of 3. So I'm going to box each of these to indicate that we have three solutions. And yes, they don't look nice, but those are the exact solutions to this system. Now, if you want to check this by graphing, if you try to graph something with a square, like if you're trying to double check your answers and you square root of 3, that's going to be really difficult to see if you got that correct. So when you're checking by graphing, you do want to use the decimal values, but it's going to be rounded. So this would be, if I put in the square root of 3, it's going to be negative 1.73-ish. And then if I put in 2 plus 3 times the square root of 3, I get 7.196. And so then I also want to get the decimal approximation of the third solution, because this will be how we check it when we graph. Because when you graph it, you're not going to be given the exact solution. The exact solution is the answer, but when you double check it, you need that decimal approximation. So I'm going to bring back up Desmos. And I'm going to actually go back a slide so I can get the systems here. So we have 3x plus y equals 2, and then x cubed minus 2 plus y equals 0. Okay, and you can see I clicked off, so now you don't really click on any of the numbers, but when I click it again, you can see the three, no, that's not a solution, the three intersection points here where they intersect. So if I go back to my other slide where I had them written with the decimal approximation, move this over. So we have 0, 2, so I've got my blue and my purple line, that's where they intersect, and negative 1.73 and 7.196. So that's not the exact answer because there was lots of decimal points, but that's the rounded answer. And then this one here, we have 1.73 and negative 3.196. So that verifies that we solved this correctly, and we ended up with 3 solutions here. Are there any questions? Okay. So the graphical method is basically when you solve by graphing and you're finding the intersection point. But this works best if you're getting whole numbers, and I only use the graphical method if it's something that I can't really solve by algebra or I'm checking my answer. So there are different possibilities here. So I just have 3 different pictures. So here we got 2 linear equations, so that gives us 1 solution. And in the middle we have a nonlinear system. We have a quadratic and a linear, so the exponent is 2, and we ended up with 2 solutions. You can see that that exponent indicates the number of solutions. Now in the third system we also have a quadratic, but I did say that it is possible for there to be no solutions if it's just right, or there's possible to have 1 solution. In this case, we have no solution because they don't intersect anywhere. If I had a quadratic and I just happen to intersect, oh, that doesn't, if I intersected exactly at the vertex, that would be 1 solution. So when you have a non-linear system, your exponent tells you the maximum possible solution. So with the quadratic here, you could have 2 solutions. You could have 1 solution if you hit it right at the vertex, or you could have no solution if it doesn't go through it at all. You can't have more than 2 solutions. That would be impossible. So now my third example here, we have y equals negative 4e to the negative x, and y plus 3x plus 8 equals 0. So this is nonlinear because we have an e and then our x is in the exponent. Now if we tried to solve this with substitution, I would replace y in the second equation with negative 4e to the negative x. But then the question is, how do you solve this? Normally, we would have to get the x out of the exponent by taking the natural log, but then if I take the natural log, I also have the natural log of x, and that's going to cause problems. So something like this can only be solved by graphing because we don't know any methods to solve this. So this must be solved by graphing. If we didn't have the 3x there, we could solve it by algebra because then we can take the natural log and solve for x. But because we have an x in the exponent and not in the exponent, we can't use our methods that we know for solving. So I'm going to bring back up Desmos, and we're going to solve this one by graphing. So I have y equals negative 4e, and then I get in the exponent negative x, and then y plus 3x plus 8 equals 0. Okay. And now I'm going to make this a little bigger. So we can't, on my graph, see where we intersect, but if I move down, we can. And if I zoom out, we verify that, okay, that's the only spot where these two are going to intersect. So our solution we have to find by graphing. And we don't know if this is the exact answer or not because it's possible Desmos rounded these values, but all we have is what Desmos is telling us. So this is the information we have about the solution, and it would be negative 0.49 comma, negative 6.53. So you would graph, it was negative 0.49 and negative 6.53. And that's all you could do. That would be the best guess you have. If you plugged those numbers in for x, if you don't get exactly 0, say if I took these numbers and x and y, let's say if I put the x value in here and I did not get exactly 0 out, if it was close to 0, like a really small number, that would indicate that these are rounded numbers. But if it came out to be exactly 0, then that would be the exact answer. But I didn't actually plug in the numbers to see if these are exact values, but because of E, and because E goes on forever, it's very unlikely that these are exact values, and it's very likely that these are rounded. And so this would not be the exact solution. It's just an approximation. Are there any questions?
One question.
Yeah.
So basically, if there's a third variable, we can only solve.
And here it's not that there's a third variable, it's that you have a variable in the exponent and outside of the exponent. That's the difference there. Yeah, so it's the placement of one in an exponent, one out of an exponent. That means you have to solve by graphing. Another option, let's see, so let me do these in red. So you have to use graphing if you have x in the, I shouldn't say x because it could be y. You have a variable in an exponent or variable as an exponent, and not in an exponent. Or if you have something like the variable is in a natural log and it's not in an exponent. A variable in the natural log or just a regular log. And also not, I should say not in an exponent, not in the natural log or log. Because the only way to solve a natural log or a log problem is by taking something to the exponent, but then that would mean what was outside is now taken to the exponent, and so now you're forced to be put into the situation where you have something in the exponent, something not, and so you kind of get in a circle between those two, and you can't get out essentially because you're just forcing yourself in one system or one option instead of the other. Nope, I don't want that browser. I'm like, one of these browsers I want to open up because I'm going to open up the textbook because the textbook has some really great examples of ones that you would have to solve by graphing. It's going to take a while because the textbook always takes forever for me to open up. But hopefully it saved where I last was. Okay, so systems of equations and inequalities. Okay, I want to actually go to the exercises. Okay. Let's see. These can all be solved. Okay, so these, let's say, use technology. Let's see, 44, that's the one that I did in an example. 43 is another one that you would have to solve by using graphing. You would not be able to solve that algebraically. And so but that one actually, exactly, if you do that, they got lucky. 45, because you have a natural log, you have an x inside a natural log, but then the x is also in a 2x, so it's not in a natural log. That would be another one where if you tried to solve that algebraically, it would be an issue, and so you would have to graph that one. Now 46 here you don't have to do by graphing, because yes, you have an x squared and a y squared and you have another squared, but we know how to solve things with quadratics. That's not going to cause any problems. What would generally happen here is that you would end up with something x to the fourth. If you replaced y, let me zoom in here so you can see this a little better. Go away. So on 46, if you solve the second equation for y and plugged it in for y squared, you'd end up with something x to the fourth. It would be difficult to solve something to x to the fourth, but it's not impossible, because then you just use the methods for, if you try to get everything to 0, have one side equal to 0, then you just use the methods for finding the zeros of polynomials, which would involve doing synthetic division and guessing and checking at where those zeros might be, using the rational zero theorem or Descartes' rule signs or those sort of things. It would be a lengthy process, but it's not impossible. But the ones where you have e to some exponent or you have the natural log, those you would have to do by graphing, because we don't have any method. Like, even if I tried to solve those and I know more techniques than you, I can't immediately come up with an easy technique to do that by hand. So that's really what you're looking for. But most of what you will see, I mean, these are very rare to encounter these types of problems. So don't worry about it too much. I just wanted to, make sure you have an idea of what it could look like. But most of the time when you have systems, most of the time they're actually linear. Very rarely do you even get nonlinear systems. And so they're usually pretty simple to solve. Does that help or make sense in any way?
Yes, thank you.
Are there other questions? Because that was actually my last example that I had for you guys. So if you have more questions.
I had maybe a quick question you can answer while you're on here about the assignment that we turned in from yesterday.
Yes.
I put it in my journal, but the graph that on the template that you gave
Was different.
Yes.
Yes. So I had some people that were having a hard time reading the graph on the original problem. And so what I did is I found a very similar graph, but the numbers are actually slightly different.
Yes.
So I put that on the template. I am grading both versions based off of whichever version you had, but going future in the course, we're going to officially change it to the graph that's in the template, because that graph is much easier to read than the one that was originally there.
Yes, okay. That's the only thing. I just wanted.
Yes. I'm the only one teaching this class, so I'm like, well, I know exactly what's going on, so I'm not going to worry too much about that. Yeah, because it is like the shape's the same, it's just in a slightly different location. But I could not find the exact graph, and I figured, well, this is close enough. At least it has the same shape. So, are there other questions? Okay. So one thing I'm taking a look at my live session. So from here, what I recommend watching next, if you're watching my instructor videos under the resources tab, is from here, I would, let's see. Well, I don't have these in the order that I wanted them. That's fine. Okay. So I would watch the multivariable systems of equations next, then the one on Gaussian elimination, because Gaussian elimination is basically the elimination method that you learn in 7.2, but we look at it in 3 variables. And my Gaussian elimination video actually goes a little bit into matrices, which we look at next week. So if you want a little preview of next week's material, that's a good one. And then the last video that I have is the modeling with systems of equations. And in that video, that is a must watch because I go through an example that is extremely similar to problem 4 on the assignment this week, which is notorious for everybody getting it wrong. So if you watch that video, you should get it 100% right because it's like almost the same thing, just different numbers. So definitely that is a must watch, the modeling with systems of equation video. And I think that's everything. Hopefully you guys watched my introduction videos that I have in the weekly content. And hopefully I'm in the process of grading your assignments, and hopefully tomorrow I should have finished grading through all of them. So crossing my fingers that I don't get interrupted. I do have a few meetings tomorrow, but I'm going to try to get all of them done tomorrow so that way you can see your feedback and see maybe if there was things that I was looking for that you didn't put, so you know for next time, or if you want to do resubmissions. So anything else? Okay, I'll call it done. Okay, so I haven't decided yet on live sessions for next week because of the holidays. That's going to be a mess, and I'm going out of town, so probably week 3 I won't have any until like maybe Monday. Oof, and then we got New Year's Eve. I may not be able to do live sessions next week, but at least I do have videos, and I'm going to try to at least record a session, if nothing else, maybe while I'm out of town if I have to. So just an update on that, but that's it. So let me know if you guys have any questions on the assignment this week. If you're not sure if you're showing enough work on the week 2 stuff, or if you have more questions, feel free to email me or call me. I'm happy to look at what you have and let you know if you're on the right track or if you're missing some steps and that sort of thing. So I'm going to pop off, and hopefully this will process quickly if I cross my fingers. And I will talk to you guys later. Thank you for joining. Thank you so much. Bye, guys.